name is Paul, and today we're going to be solving this question from the Raphael and Woods textbook. So, given an image of size m times n, it's just image, I'll just write it. You asked to perform an experiment. Basically, you're going to apply a Gaussian low pass filter with a cutoff frequency of d naught. Let C min denote the smallest positive number representable in the machine in which the proposed experiment will be conducted. And the first question, can you predict what the resulting image will be for a sufficiently large value of k? Okay, so what is the result? So this is a bit tricky, but I'm here to help you out. First thing you should know is that when you're applying a filter, just like a Gaussian low pass filter in frequency domain, the DC component is at the center of the frequency spectrum. Now, the DC component is basically the average intensity of the entire image. So now for a Gaussian low pass filter, I'll just say GLPS. For Gaussian low pass filter, the frequency value at the DC, that's the center of the spectrum, this is the formula for the Gaussian low pass filter in the frequency domain. At the center of the frequency spectrum, the value of the Gaussian low pass filter will always be 1. And every other place, it will be ranging from values greater than 0 to values less than 1. So here could be 0.9, here could be 0.5, and so on and so forth. So if you want to apply a filter to an image, the formula is actually this. G of V, which is the filtered image, will be H of V, that's the Gaussian filter, times, that is convolution of the image itself. So if you apply this a k number of times, you're simply just going to raise this to the power of k. Now, remember I said at the center, where the DC component is, the value, no matter how many times you apply that Gaussian filter, the frequency at that point will still remain 1. Even if it's 1 raised by 1010, it doesn't matter. The value will still be 1. However, for other frequencies in the spectrum, let's say for 0.9, that's the Gaussian low pass value of this particular place, and you want to apply it a k number of times, let's say 50. If you punch this into the calculator, you're going to get 0.005153. You see, the frequency component is as good as 0 already. If you do it for all that parts, you're going to notice everything. The frequencies at those places are becoming to be 0, except the one at this point. Now, when you want, because this is in the frequency domain, now when you want to view the image, you're going to take it to the spatial domain. So in the spatial domain, the code is going to use only the DC term to rebuild the entire image, because that's the only place where it sees a frequency of 1. The other places are 0. So basic component is going to be used to rebuild the entire image. And remember what the DC is. The DC is the average intensity of the entire image. So basically, at every point in this rebuilt image, it's going to be the exact same color, the average intensity of the entire image. Therefore, the answer to these questions, if you apply the Gaussian filter for a very sufficiently large value of k, at some point you're only going to have a constant image, an image with a uniform gray color, which is not changing, it's just the same color from top to bottom. So that's just the answer to this question. Okay, so now let's move on to B. So it says to derive an expression for the minimum value of k that will guarantee the result that we predicted. So basically the image becomes constant, that is all other components except this component at the center of the spectrum has a frequency value of 0. So in order to do that, write out our formula. H of V, this is the Gaussian low pass filter. Use the formula for it in the frequency domain over 2 d square naught, where d naught is the cutoff frequency we're given. D is d u comma v square, is basically the distance from the center of the spectrum to a point u of v in the frequency spectrum. You'll see why that's important later. Now, if you apply this a k number of times, it's basically just going to be h raised power k u comma v equals to k times k d u v square over 2d square naught. For the repeated filtering, that is a k number of times, for it to match what we predicted in A, we need all non-DC frequencies, that is all the frequency spectrum apart from the DC frequency. We need all non-DC frequencies to become so small, that's like 0.00000, so small that the computer can no longer even represent it anymore. And in the question, they say let seeming denote the smallest possible number representable in the machine. So we want to go to a value less than this seeming so that the computer can no longer represent it. That means it doesn't exist. That means it becomes basically almost like zero. So the formula is basically we want to apply the Gaussian filter so many times that it becomes less than the least representable number seeming. We're going to add 0.5 instead of just mean, because to make sure that the frequency of the non-DC components are pushed below the smallest representable number. So it's kind of like just a safety margin, a stricter safety margin. So now we're basically just going to solve KD u comma v square over 2d naught square 0.5 seeming. Basically going to take the ln of both sides so that we can cancel out this e exponential here. Let's take the ln of both sides. That's going to lead us to the equation. Sorry, I forgot to add negative here. That is all negative. So it's going to be negative kd u v square all over 2d square naught less than ln 0.5 e mean c mean. Now I'm simply going to multiply both sides by -1 just to cancel out the minus in there. I don't want the minus to be where the k is. Just by -1. When you multiply both sides of an inequality by -1, the sign will flip. So it's going to be u comma v over 2d square. 2d square naught. The sign is going to flip to be 0 point minus ln 0.5 c minimum. Now make k subject of formula. I'm just going to come down here and continue that. K will be greater than 2d square naught over d u v square ln 1 over 0.5 c minimum. So I just used a ln rule here, which is a negative. If you can take the inverse of the value, it's the same thing as what you have here. So moving on, in order to find now in order to find the true minimum value of k that such that the Gaussian low pass filter wipes out all the non-DC components, that is all these other components in the frequency spectrum. In order for you to really find the minimum value of k, you have to find the smallest non-zero distance from the origin. Now the question is why? That's because the frequencies closest to the origin are actually the hardest frequencies to wipe out. That's because, as you can see from the formula for the Gaussian low pass filter, as the distance from the origin increases, this is distance of 1, this is distance of 2, but let's work with distance of 1 first. Now for a distance of 1, that's maybe e raised power negative 1, the value of h is going to maybe be around 0.367. For a distance of 2, that's e raised power negative 2, the value for h is going to be 0.135. So you can basically just see that the value of the Gaussian low pass filter is decreasing. with an increase in distance. So the value at this point closest to the origin, that's the DC component, closest to the origin, will be the hardest, because it will be the hardest frequency to actually get rid of. It's going to be the one that will have the highest frequency. Then as you increase distance, it has a lower frequency, which means it's going to go down to zero much faster. So that's just the whole idea. So that's why for the value of DUV, that is, as I told you from the beginning, the distance from the center to a frequency point UV. The reason why we're going to choose the smallest non-zero distance from the origin is because I've already explained that to you. So the smallest distance from the non-origin is going to be 1. So that will be k greater than 2d squared 0. 1 raised by 2 is basically just 1. So 1 over 0 0.5 c minimum. This is basically saying that the number of times k that this filter has to be applied for this image to become constant must be greater than whatever you solve here. So that's essentially the answer to this question. Anything you do not understand, please do not hesitate to ask it in the comment section. Thank you for listening.